Welcome, data engineers and architects. Let's get started on our journey to mastering ACID compliance in Apache Spark using Delta Lake. Welcome. Today we are diving deep into working with Delta Lake to achieve robust ACID compliance within Apache Spark. Traditionally, data lakes are simply massive collections of raw files distributed across cloud storage. This makes them highly prone to data corruption if a Spark job fails mid-write, or if multiple jobs attempt to modify the data concurrently. Delta Lake solves this by sitting directly on top of your existing cloud storage and acting as a protective, intelligent layer. It brings ACID transactions which relational databases have relied upon for decades right into your distributed Spark environment. This means no more dirty reads, no more corrupt partitions from failed jobs, and seamless unification of your batch and streaming data pipelines. As we progress through this training, you will learn exactly how Delta Lake achieves this, how to optimize your tables using advanced clustering, and how to apply it in real-world, enterprise-level architectures. Let's take a close look at this architectural flow diagram to understand exactly where Delta Lake fits in. Instead of your Apache Spark engine interacting blindly with raw Parquet files in your data lake, it now routes all read and write operations through the Delta Lake layer in the center. This layer is responsible for managing a highly structured transaction log. When a Spark job finishes processing, Delta atomically commits the transaction to your cloud storage. If the Spark job crashes or fails for any reason, the transaction is completely rolled back, keeping your storage perfectly clean and uncorrupted. This abstraction layer is completely transparent to the user, meaning you get enterprise-grade reliability without having to completely rewrite your existing Spark SQL or data frame code. Let's break down the fundamental basics of ACID compliance and understand exactly why it is a massive game changer for Spark. The A stands for atomicity. It guarantees an all-or-nothing operation. If your Spark cluster crashes during a massive terabyte scale write, you will not be left with half-written, corrupted files. C is consistency, meaning any read query will always see a valid state of the data, never a chaotic midway state. I is isolation. Previously, concurrent writes in Spark were incredibly dangerous. Delta Lake allows multiple independent Spark jobs to write at the exact same time safely using optimistic concurrency control. Finally, D is durability, ensuring that once a job succeeds, the data is permanently and safely committed to your cloud object store. Together, these pillars transform a raw data lake into a reliable lakehouse. In this block diagram, we visualize the 4 pillars of ACID that Delta Lake actively injects into your Apache Spark environment. Atomicity blocks partial writes from entering your downstream pipelines. Consistency blocks dirty reads, ensuring analysts always see the truth. Isolation safely manages concurrent Spark pipelines, preventing write conflicts, and durability ensures your data survives catastrophic cluster failures. Notice how all 4 pillars feed directly into the central Delta Lake engine. By enforcing these rules strictly, Delta Lake guarantees that your downstream systems receive only reliable, production-ready Spark analytics, completely eliminating the need for complex, manual data validation scripts. You might be asking yourself, why shouldn't I just use raw Parquet files? While Parquet is an incredibly fast columnar format, it is ultimately just a file format. It does not know if a Spark job crashed, and it definitely cannot enforce strict schemas across multiple independent jobs. If one team writes a string into a column instead of an integer, your downstream analytics immediately break. Delta Lake solves this by wrapping Parquet with a transaction log. It rigorously enforces your schema on write, actively blocking bad data before it corrupts your tables. Furthermore, Delta Lake automatically addresses the notorious small file problem that plagues long-running Spark streaming jobs. As a massive bonus, it introduces time travel, allowing you to effortlessly query historical versions of your dataset or roll back mistakes with a simple Spark SQL command. This comparison diagram sharply illustrates the stark differences between legacy data lakes and Delta Lake. On the left side, a Spark job writes directly to raw Parquet. Because there is no schema check, invalid data flows freely, leading straight to corrupt downstream data and broken dashboards. Now look at the right side. When Spark uses Delta Lake, the transaction log acts as a strict gatekeeper. It enforces the schema in real time. If the data is invalid, the job safely fails and your existing data is fully protected. Only fully validated, complete data ever makes it into your clean Parquet files. This shifts your engineering focus from constantly fixing broken data to building new features. Let's dive under the hood to see exactly how Delta achieves ACID compliance for Spark. The absolute brain of a Delta table is the _delta_log directory. When Spark writes to a Delta table, it does not just dump Parquet files, it writes a structured JSON commit file into this log directory. This JSON file acts as an immutable ledger, recording exactly which Parquet files were added and which were logically removed. When a Spark reader comes along, it completely ignores the data files at first. Instead, it consults this transaction log to get the exact, current blueprint of the table state. To prevent this log from slowing down Spark over millions of transactions, Delta periodically rolls up the JSON files into a highly compressed Parquet checkpoint file, ensuring metadata processing remains incredibly fast. Look at this storage directory diagram. At the root of your data lake storage, you have the Delta log folder sitting right alongside your actual data partitions. The Delta log contains sequential JSON commit logs and a consolidated checkpoint file. The magic happens because Spark is programmed to ignore the raw Parquet files completely until it parses the transaction log. The log explicitly dictates which Parquet files are valid, which are obsolete, and what the schema currently is. By managing state via these tiny JSON ledgers, Delta makes ACID transactions highly scalable on cheap, distributed cloud storage. Before Delta Lake, updating or deleting specific rows in a Spark data lake was an absolute nightmare. It usually required you to read the entire partition into memory, modify the data, and completely overwrite the partition on disk. Delta changes everything by bringing standard SQL DML operations directly to Spark. You can now execute targeted updates, deletes, and complex merges, commonly known as upserts. This is absolutely essential for modern data pipelines, especially when handling GDPR right-to-be-forgotten requests. How do we do it? We simply use the Delta Table API in PySpark, Scala, or standard Spark SQL. Under the hood, Delta uses an elegant copy-on-write mechanism. It does not modify existing files in place. Instead, it writes new Parquet files with the updated data and records the old files as logically deleted within the transaction log. This sequence diagram beautifully maps out the lifecycle of a merge operation in Spark. First, the Spark execution engine reads your incoming source data and cross-references it with the Delta transaction log to pinpoint matching records. Once identified, Spark writes entirely new Parquet files containing the merged and updated data. Finally, a new commit is written to the Delta log, atomically swapping the old files for the new ones. Because of ACID consistency, any concurrent readers querying the table during this exact process will continue reading the old files until the commit is fully finalized. This guarantees that your analytics dashboards never crash due to a file not found error. Once the transaction commits, the next reader automatically picks up the fresh data. As a senior engineer, you must master Delta Lake optimization. Frequent streaming inserts or complex updates generate thousands of tiny Parquet files. This small file problem destroys Spark's read performance. The solution is the optimize command, which seamlessly integrates with Delta Lake to compact small files. But we take it a step further with Z-ordering, also known as liquid clustering. Liquid clustering shines in range-based queries, particularly in Delta Lake environments, by reducing unnecessary data reads. When you run optimize with a Z-order by clause, Delta physically collocates related data into the same files. This improved data skipping means queries only scan the relevant sections of data, reducing I/O operations and speeding up execution. Liquid clustering works in conjunction with Delta Lake optimizations, such as optimize and vacuum, to improve query speeds while maintaining clean storage. This allows Spark's Catalyst Optimizer to drop execution time dramatically. Observe this optimization workflow. We start on the left with a chaotic Delta table heavily fragmented by small files and scattered data points. We trigger the optimize sorter by command. Spark reads all these small files and rewrites them into large, optimized Parquet blocks. Notice how the clustering process ensures that specific column values are perfectly grouped together. Because of this intelligent liquid clustering, subsequent Spark SQL queries can instantly bypass irrelevant blocks via extreme data skipping, yielding massive performance gains and significantly lowering your compute costs. Let's tie everything together with a highly critical real-world use case, building a change data capture, or CDC, pipeline for a global financial application. The core challenge is ingesting a continuous stream of database updates such as inserts, modifications, and strict GDPR deletion requests into our data lake, while simultaneously serving consistent data to our BI reporting tools. If we used raw Parquet, the table would lock during updates, or analysts would read corrupted, half-written data. By utilizing Delta Lake, our Spark structured streaming job continuously applies a merge into command. It applies the inserts, updates, and deletes seamlessly. Meanwhile, thanks to ACID isolation, our BI tools can currently query the exact same Delta table. They experience zero downtime and zero dirty reads, unlocking true real-time analytics. Looking at this real-time architecture diagram, you can clearly see the power of Delta Lake in action. On the far left, raw CDC events stream continuously from our operational database into Apache Spark. Spark executes a micro-batch merge operation against the centralized Delta table. Because Delta intelligently handles the ACID transaction log, the table is updated safely and atomically. On the right side of the diagram, business analysts and data scientists are actively running massive aggregation queries via their BI tools. Delta's snapshot isolation guarantees that they always query a perfectly consistent version of the data. They are completely unaffected by the continuous streaming updates happening in the background, proving how Delta bridges the gap between streaming and batch workloads. To wrap up our session, integrating Delta Lake is the absolute gold standard for achieving ACID compliance and data reliability in Apache Spark. It transforms your fragile data lake into a robust lakehouse. As a best practice, remember to regularly run the optimize command to prevent small file bottlenecks. Also, because Delta's copy-on-write mechanism retains old files for time travel, you must periodically run the vacuum command to permanently delete obsolete files and minimize your cloud storage costs. Always measure query execution time before and after Z-ordering to assess improvements and validate your performance gains. Thank you for joining me in this deep dive. Please invite your colleagues to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final lifecycle diagram summarizes the absolute best practices for Delta table maintenance. The cycle begins with continuous data ingestion via Spark. Next, we execute our merge commands to apply business logic. Crucially, we schedule routine optimization jobs using Z-ordering to keep query speeds lightning fast. Then, we implement a vacuum schedule to purge dead files and optimize cloud storage costs. This perfectly maintained, endless cycle ensures your Spark analytics remain highly performant, fully compliant, and extremely cost-effective.